Give reasons for the following. Ionic compounds have a higher melting and boiling point. Let us see what are ionic compounds. Example like sodium chloride. Sodium chloride is made up of sodium, positive ion, and chlorine, negative ion. Now between this positive ion and this negative ion, there is a strong force of attraction. And hence a large amount of heat is needed to break this force of attraction. Large heat is needed to separate the sodium and the chlorine. So these are the points you need to write. Is first, they have a high melting and boiling point because ionic compounds, the oppositely charged ions are held together by strong ionic bonds, and these strong ionic bonds require a lot of heat to break these bonds, and hence they have a high melting and boiling point. Sodium is kept immersed in kerosene. Now sodium, the first point is sodium is highly reactive, and if it is exposed to air, it quickly catches fire. It burns in air. So it is put in kerosene to cut off the supply of sodium with air. So if you have, how is sodium stored? If you have a beaker, in this beaker you will add kerosene, and then sodium is stored at the bottom of this beaker here. So it cuts off the supply of air. The air cannot come in touch with kerosene, with sodium. Here is sodium. If it comes in direct contact with air, if it is kept out in the open, sodium will react with oxygen, and it catches fire because it's highly reactive. Reaction of calcium with water is less violent. Now when calcium reacts with water, it gives calcium hydroxide plus hydrogen. But however, when sodium reacts with water, it also gives sodium hydroxide and hydrogen. But there is a difference. Since sodium is more reactive, it gives a large amount of heat. And this heat, because of this heat, the hydrogen catches fire. And the reaction is very violent. Because the hydrogen, there's lots of fire around the hydrogen, and it's a very violent reaction. But since sodium is less reactive, here there is less heat. And this heat is not sufficient for the hydrogen to catch fire. So this is exactly what we are going to write. Is less violent because the heat evolved is insufficient. There's insufficient heat to burn the hydrogen gas. Heat is given out and hydrogen gas is also given out, but the amount of heat is not sufficient to burn the hydrogen gas. Generally, no hydrogen gas is evolved when metals react with nitric acid. So let us see what happens when metals react with an acid. We'll take an example of potassium reacts with an acid, say HCl, or say nitric acid. You get potassium nitrate plus hydrogen. That is standard with nitric acid. This is what you expect, because even when it reacts with potassium reacts with HCl, you get HCl plus hydrogen. Okay, but now when it comes to nitric acid, something extra happens, because nitric acid is an oxidizing agent. What do you mean by oxidizing agent? It gives out oxygen. So it gives out oxygen, and this oxygen now reacts with hydrogen, and the hydrogen now forms water. with this oxygen. It reacts with this oxygen given out by nitric acid and forms water. And nitric acid itself, after giving out the oxygen, will form oxides of nitrogen. So with nitric acid something different happens. Hydrogen gas is not given out, but instead we get water. So we'll read that. Nitric acid is first a strong oxidizing agent. Second, it oxidizes the hydrogen formed into water and itself gets reduced to an oxide of nitrogen. Sodium oxide solution cannot be kept in aluminium container. Now when we have sodium hydroxide and it is kept in an aluminium container, it reacts with that aluminium to form sodium aluminate plus hydrogen. So as time passes, this aluminium container will get corroded because it is reacting with the substance kept inside it. So here the answer to this first point is that sodium hydroxide is a strong base. Now when it is kept in an aluminium container, it reacts to form sodium aluminate with hydrogen gas, and hence the container gets corroded. Aluminium reacts with hydrochloric acid slowly in the beginning. The reaction with aluminium with hydrochloric acid is very fast because aluminium is very reactive. So you get aluminium chloride plus hydrogen. Fast, reactive. Aluminium is a reactive metal. But usually the reaction first comes slow because aluminium being reactive, it always has a coating of aluminium oxide. It reacts with the oxygen outside. So this strip of aluminium, when exposed to the air, will always have a protective covering of aluminium oxide. So now when you react this strip with an acid like hydrochloric acid, first the hydrochloric acid will have to react, point 1, it helps to react with the aluminium oxide which is around it, the protective covering of aluminium oxide. This is a slow reaction. And then in the next step, once all the covering is gone, then the hydrochloric acid will react with the aluminium. Now this reaction is fast. So in the beginning, the hydrochloric acid will react with this coating and all this coating will go away. And the reaction is slow in the first step. And next, when it reacts with the aluminium, then the reaction becomes faster. So aluminium metal has a layer of aluminium oxide or alumina on its surface, which is highly stable compound, which slows down the reaction first when reacting with the acid. Name a solvent in which electrovalent compounds are soluble and a solvent in which they are insoluble. Now to remember, electrovalent compounds are ionic compounds. And in your textbook, here's a picture from your textbook from page 49. Here it's given electrovalent compounds are generally soluble in water. So they are soluble in water and they are insoluble in solvents like kerosene and petrol. So insoluble in kerosene and petrol. They do not dissolve. So here that's what is written here now. Here we have water is a polar solvent. This is made up of a slight charge and also known as ionic compounds are soluble, in which they are soluble. But ionic compounds are not soluble in petrol, which is an organic compound, and it is non-polar. They are insoluble in petrol. Why calcium floats in water? We go back to the reaction of calcium. Calcium with water gives you calcium hydroxide plus hydrogen. So when you have a beaker of water here and you add, this is a beaker of water, and you add calcium to it, here you add calcium to it, this hydrogen that is formed will begin to stick around the calcium. And because it sticks around the calcium, this hydrogen will stick on this calcium. And then the calcium then begins to float. So let's read this now. Calcium is heavier than water, which should sink it in water. You expect it to sink in water. But when calcium is dropped in water, it floats because it reacts with water to form hydrogen gas. And due to the sticking of hydrogen bubbles on calcium metal surface, it starts floating. Write any two properties of ionic compounds. They are hard crystalline solids. Second, they have high electrostatic force of attraction, thus high melting and boiling point. And to add more points on the third one, we can say they conduct electricity only in molten state. In molten state or in aqueous state. You can refer to page 49 for more properties. Show the formation of aluminium chloride by the transfer of electrons between atoms if aluminium and chlorine are 13 and 17. In the first part, we already here they have already given, and this is at aluminium 13. So you know it is 2, 8, 3, which means aluminium now will lose 3 electrons and become aluminium plus 3 electrons. So this is what happens here. It loses the 3 electrons. Those 3 electrons are now accepted by chlorine, and we know chlorine is 17, so it is 2, 8, 7. So chlorine does what? It gains 1 electron to become chlorine negative plus, not plus, it gains an electron. So in this case, have you seen, you have aluminium, and aluminium has got these 3 extra electrons, 1, 2, 3. These electrons are then transferred to 3 chlorine atoms to give you aluminium chloride. Each chlorine has got 1, 2, 3, 4, 5, 6, 7. And this 8th one that has come is from aluminium. Here too it has got 1, 2, 3, 4, 5, 6, 7, and the 8th one has come from the aluminium. Here too 1, 2, 3, 4, 5, 6, 7, 8, and this 8th one would have come from aluminium. So one aluminium atom supplies to 3 chlorine atoms, because this aluminium has got 3 in the outermost orbit. It supplies to each of these chlorine. What are amphoteric oxides? Give an example. Now, metal oxides which show basic as well as acidic behavior are known as amphoteric oxide. One example is aluminium oxide. Here it reacts with an acid in this first case, and in the second case it reacts with a base. So therefore it's called an amphoteric oxide. There are two examples. There is aluminium and there is also zinc. This is also an important part, and it's on your page 41 of your textbook. Amphoteric oxides, they react both with acid as well as with base. What is observed about 1 hour of addition of strips of copper and aluminium separately to ferrous sulfate? So let's write that out. So in the first case we are adding copper to ferrous sulfate, and in the second case we are adding aluminium to ferrous sulfate. So in the first case no reaction will take place, and it's because copper is less reactive than iron. So copper cannot displace iron. So here no reaction. But when it comes to the second, here we have aluminium is more reactive than reactive than iron. So aluminium will displace iron. So when it will displace iron, and what will happen is you get aluminium plus FeSO4 to form aluminium sulfate plus 3Fe. Another point to remember is this is green in color. Aluminium sulfate is green in color, and this green color disappears. Putting copper strips in FeSO4, no reaction, because copper cannot displace iron from FeSO4. Putting aluminium strips in FeSO4, we get a green FeSO4 disappears. The iron metal is settling down at the bottom of the beaker. These reactions are called the displacement reactions. So this iron that is formed here will now settle to the bottom. Show the formation of magnesium oxide. So we have magnesium, it is 12, atomic number, configuration 282. So what happens to magnesium is it is 282, it loses an electron, loses 2 electrons and forms magnesium 28 plus 2 electron. On the other hand, oxygen is 26, so it gains 2 electrons and becomes oxygen minus 2. So when magnesium has got these 2 electrons, and we know oxygen has got 6, and magnesium now will give here these electrons to oxygen, and then you will form magnesium oxide with 1, 2, 3, 4, 5, 6, and these 2 are from magnesium. So this is magnesium oxide. Formation of magnesium oxide, you have Mg plus 2 and oxygen minus 2. So here the first point you need to write is atomic number of magnesium is 12, its configuration is 282, and the atomic number for oxygen is 8, configuration is 26. Then the next is, in order to complete the octet, oxygen will gain 2 electrons from magnesium, and thus formation of an ionic bond between magnesium and oxygen. How will you show that silver is less reactive than copper? So for this, first we will take two test tubes. We'll take test tube 1, and in test tube 1 we will put copper plus silver sulfate, and in test tube 2 here we'll put silver plus copper sulfate. And after some time you will notice that in this test tube the silver sulfate is like white in color. Here the reaction will take place in this test tube because copper is more reactive. You will get copper sulfate plus silver, and this white color will now change to blue because copper sulfate is blue. But in this here you will find this is blue color, and the blue remains blue only because no reaction takes place. Now why does in the second test tube no reaction takes place? Because silver cannot displace copper, because silver is less reactive than copper. But in the first test tube, here in the first test tube we see that copper displaces silver because copper is more reactive than silver. So we'll just read this up. So first we take in test tube 1, we take silver sulfate solution which is white in color, and in test tube 2 we take copper sulfate solution that is blue in color. And then they add this, in test tube 1 you add copper, test tube 1 you add copper turnings in test tube 1, and in test tube 2 you add silver, and keep it undisturbed for some time. What you will observe that in test tube 1 has changed from white to blue, whereas in test tube 2 no change in color. So this very clearly indicates that copper displaces silver from a silver sulfate solution and forms copper sulfate, and in test tube 2 nothing happens, no displacement reaction takes place. Hence we can prove copper is more reactive than silver. So let me just go over it again. So when you have copper with silver sulfate, and then you have silver with copper sulfate, here reaction takes place, here no reaction takes place because the silver cannot displace copper. You're given a hammer, battery and a bulb, wires and a switch. How would you use them to distinguish between samples of metals and non-metals? Assess the usefulness of this test in distinguishing between metals and non-metals. So in the first you will arrange a circuit diagram and you will put the sample in between here, the sample. If there is current passing, if current begins to pass, if it's a conductor, current will pass and the bulb will glow, then you can say it is a metal because metals conduct electricity. But on the other hand, if you put and there is no current and the bulb does not glow, that means it is a non-metal because non-metal do not conduct electricity. So here they have said set up an electrical circuit shown below, then insert the sample to be tested between the clips A and B. If the bulb glows, the sample is metal, and if the bulb does not glow, the sample is a non-metal. Thus metals are good conductors of electricity, non-metals are poor conductors of electricity. And then we can also use a hammer. Here we use a hammer. If a substance produces a sound when struck beating with a hammer, it is a metal. But if there is no sound produced, it is a non-metal. because we know metals are sonorous. They produce a sound when they're beaten by a hammer, and non-metals are non-sonorous.